Gentlemen, it's a pleasure to welcome you to the third day of the centennial celebration of Bose-Einstein statistics, a legacy of Dhaka, jointly hosted by Department of Physics and the Bose Center for Advanced
Recording in
Study
progress.
and Research in Natural Sciences in Dhaka University. We are beginning the conference's seventh session and second online session. Today, we are honored to have Nobel laureate Professor William D. Phillips as a conference speaker. Professor Phillips is renowned for his Nobel-winning work for the development of methods to cool and trap atom with laser light. So following him, Professor Jo Gyu Bung from Hong Kong University of Science and Technology will present as a keynote speaker. This session is chaired by M. Zahid Hasan, Eugene Higgins Professor of Physics at Princeton University, USA. I now invite Professor Zahid Hasan to proceed.
Thank you. Thank you. I thank the organizers for putting together this wonderful session, and thank you for inviting distinguished speakers to address throughout the conference. And we are extremely lucky and grateful to Professor Bill Phillips to be joining us today, this morning. And most of you already know Bill. He doesn't require introduction. He's one of the key pioneers of the field of laser cooling of light or photons. The photons are bosons, so the laser cooling, the physics behind laser cooling has the Bose statistics built in there, and the laser cooling led to the technology. This is the key technology behind achieving BEC of atoms and later molecules. So he's also a pioneer along that line. So he has a number of wonderful publications, and that that manifests the physics of this quantum statistics. So he's really an experimental physicist who laid the foundation of actually seeing these quantum statistics coming out in reality. It's the lab realization of this kind of physics. So we are extremely happy and grateful to have Bill join us today. So without further ado, I would invite Bill to present his talk. Thank you, Bill. Welcome.
Thank you. Thank you for that kind introduction. It's a pleasure to be here remotely in Dhaka, such a historic place as we get ready to celebrate the 100th anniversary of the beginning of quantum mechanics. One of the most important aspects of quantum mechanics was developed right here, of course, by Satyendra Bose. So I'm going to talk to you today about the subject of the development of the ideas that were introduced by Bose in 1924, the idea of quantum indistinguishability and quantum statistics, through to the achievement of Bose-Einstein condensation and all of the things that were needed to have that come about. I am a member of the Joint Quantum Institute, which is joint between the National Institute of Standards and Technology and the University of Maryland. And at NIST, I'm part of the Laser Cooling and Trapping Group. And here you see the permanent members of the Laser Cooling and Trapping Group. And I particularly want to mention Gretchen Campbell, who is my group leader and an important contributor to the science of Bose-Einstein condensation herself. The story, I do want to remind you that you should think of questions. I'm going to stop several times during this lecture to receive your questions and also to ask you some questions. I'm hoping that there will be some people, especially people who are historians, who will be able to answer some of the questions that I came up with as I was preparing for this talk. Now, I want to begin with a story that I think you've heard many times, but it's such a wonderful story that I think it is worthwhile repeating. In 1924, uh, Bose came up with the idea that photons are indistinguishable, and as a result, the number of states that you can have to reflect a certain macroscopic state of photons should be counted in a way that is different from the way in which people like Boltzmann and Maxwell taught us to count. And using this new way of counting and this new understanding of indistinguishability, he was able to derive Planck's radiation law, the law of blackbody radiation, in a way that was far more natural than the way in which Planck had been able to do it. He wrote a paper, submitted it to the Philosophical Magazine, a place where he had published papers in the past, and the paper was rejected without even being sent out for refereeing because the paper was so groundbreaking that the editors of Philosophical Magazine did not understand it and didn't understand its significance. And here I have to really admire Bose because he had the courage to send his paper to Einstein, who by this time was one of the most famous scientists of all time, let alone one of the most famous living scientists. And Einstein read the paper and immediately realized how important what Bose had done was. Einstein translated the paper, which Bose had written in English for submission to PhilMag. Einstein translated the paper into German and submitted it on Bose's behalf to Zeitschrift für Physik, one of the top physics journals of the time. And then, and this is the thing that's the subject of much of the rest of this talk, realizing how important what Bose had done was, Einstein extended Bose's ideas to include not just photons, but atoms. And in doing that, he was able to come up with the idea of Bose-Einstein condensation, as we call it today. Well, here is the German version of the paper that Einstein translated on Bose's behalf. The title translates to Planck's law and the light quantum hypothesis. And in that paper, Bose ends the paper with this formula, which is the famous formula of Planck's law of blackbody radiation. And the German translation of this last phrase is which equation is equivalent to Planck's formula. And then it notes that it was translated by Einstein. But then there is this translator's note at the very end, and I give the English translation with the help of Google Translate, says that Bose's derivations of Planck's formula represents, in my opinion, this is Einstein speaking, an important advance. The method used here also provides the quantum theory of the ideal gas, as I shall explain elsewhere. And that, of course, is what we know as Bose-Einstein condensation. Now, as I've said before, what Bose understood was a different way of counting the number of microscopic states that correspond to a macroscopic state. This is at the heart of the statistical physics that was pioneered by people like Boltzmann and Maxwell. And Bose conceived of a different way of counting those states, one that depended on this new concept of indistinguishability. Boltzmann's way of counting implicitly assumed that all the particles were distinguishable, while Bose's way of counting treated them as intrinsically indistinguishable. And what that meant was that, for example, if you have two particles in two different locations, putting one particle here and one particle here is no different than switching them around because the particles are absolutely indistinguishable. And that changed everything. Now, indistinguishability is not an entirely new idea. In the 19th century, Lord Kelvin was thinking about indistinguishability, but not as deeply as Bose did. he was recommending that the vibrations of atoms. Now, remember, this is the 19th century. Many people didn't believe in atoms at the time, but he thought that what he called the vibrations of atoms, what today we would call the difference in energy levels of atoms, would make a superior standard of time instead of the rotation of the Earth. And what Kelvin wrote was that atoms of hydrogen or sodium, ready-made in infinite numbers, are all absolutely alike in every physical property. So he's expressing early in the 19th century this idea of indistinguishability, but it really makes me wonder, how did he know that? How did he know that all sodium atoms were absolutely alike? This is at a time before people believed in atoms, well before quantum mechanics, which has led us, pioneered by Bose, to understand the full meaning of indistinguishability. But we might wonder what genius inspired Kelvin to believe that all atoms of sodium were absolutely identical. And we might also wonder what genius inspired Bose to understand the significance of that indistinguishability for the way you should count in statistical mechanics. And we might also be in awe of what Einstein knew he should do next to extend the ideas that Bose had. Well, here's the introduction, the title of Einstein's paper. This was actually a paper that was a written version of a presentation at a meeting. In fact, this is a meeting of the Prussian Academy of Sciences, as you see here, the general meeting of the 10th of July. The submission date for Bose's paper was the 2nd of July. So this is just 8 days after Einstein submits Bose's paper to Zeitschrift für Physik. He's speaking to the Prussian Academy of Sciences about his extension, the quantum theory of monotonic ideal gases. So what was it that Einstein did with this new insight that Bose had? Well, he considered a gas of atoms, which I show here as a kind of cartoon. The atoms are moving around with different velocities, and one of the key differences is that in thinking of atoms, the atom number is conserved. Einstein imagines that the atoms are in thermal equilibrium, say with the box in which they are, but the atoms are not lost. This is very different from the situation with photons. Photons that are in equilibrium with some container that they're in can be absorbed by the container and they can be re-emitted. So the number of photons is certainly not conserved. And if you cool the box down to make the temperature lower, then the number of photons goes down. Whereas if you cool a box of atoms, the number of atoms stays the same as long as the atoms don't stick. And we assume that this is an ideal gas, so things don't stick to each other. So that was one of the key differences that Einstein had compared to what Bose was thinking about. And what he found was, using the insights that Bose had given, using this new idea of quantum statistics that Bose introduced, he found that as he added more atoms to the box at a given temperature, that at some point the states that were at non-zero velocity were in a certain sense filled up. And if you put more atoms in, those atoms had to go in at zero velocity. This represented a phase change, a phase transition, which we now call Bose-Einstein condensation. The point at which, when you add atoms to the box of gas, that those atoms go into the ground state, that they go into the lowest energy state, which, in the absence of a quantum mechanical description of the motion of the atoms, would be at zero velocity. Now, I want to emphasize for a moment how strange this is. Up until this time, people had studied phase transitions in gases, the condensation of steam into water, for example, is a phase transition that people were familiar with. But that phase transition and all other phase transitions that were understood to occur in a gas happened because of the interactions between the atoms. The reason why a gas, a water vapor, turns into a liquid is because the molecules of water vapor stick together. It's because of the interactions. Einstein was treating an ideal gas. When I was young, I was taught that ideal gases did not have phase transitions, but they do. In the case of Einstein's study of a gas of what we now call bosons, there is a phase transition that happens even though there are no interactions between the atoms. And this was the result that Einstein came up with, that the critical temperature at which this phase transition happens is some constant which can be determined uh, from this. This is the Riemann zeta function times something that's proportional to the 2/3 power of the density of the gas, and inversely proportional to the mass of the atoms. So that means a small mass would lead to a higher critical temperature, and a higher density would lead to a higher critical temperature. So these are the basic facts of Bose-Einstein condensation as Einstein conceived it. And just to give you an idea of the kinds of temperatures and densities that we're talking about, today, one of the most common atoms that is used to make an atomic gas Bose condensate is rubidium. If I have a rubidium gas with a density of 10 to the 14 atoms per cubic centimeter, now I remind you that air has a density of about 3 times 10 to the 19 molecules per cubic centimeter. So 10 to the 14 atoms per cubic centimeter is sort of a modestly good vacuum, but it's a lot of atoms in this context. That will have a critical temperature of 300 nanokelvin. Now, 300 nanokelvin is incredibly cold. Now, you might ask, why can't we make the density bigger? Well, there's real problems with making the density bigger, and we'll get to that in a moment. So you can't have densities much bigger than 10 to the 14. That means we're going to have a really, really cold temperature. And this is the reason why, one of the reasons why we haven't had Bose condensation until relatively recently, 1995. Well, that's 25 years ago. It may not seem, that's almost 30 years ago. That may not seem like so recent to you, but compared to 1924, when this first came out, it took a long time before it happened. Now, I want to introduce another way of thinking about the nature of Bose-Einstein condensation, that is the condition under which Bose-Einstein condensation happens. We recall that around this time, it was discovered by de Broglie, or at least Louis de Broglie proposed that atoms should be treated as having wave-like character. And the wavelength of this wave-like character, which we call the de Broglie wavelength, is equal to Planck's constant divided by the mass times the velocity of the atoms. In other words, it's Planck's constant divided by the momentum of the atoms. And Einstein's phase transition, Bose-Einstein condensation, happens when the atom's density is high enough that their average spacing is about equal to this number, the de Broglie wavelength. Now, this is not the way that Einstein thought about this, at least as far as I understand, but it's an equivalent way of thinking about it, and you might think of it in the following way. When the wavelengths of the atoms overlap, then you can't distinguish one atom from another by its position. And it's the indistinguishability of the atoms that makes all these wonderful things happen. And this is just the place where quantum indistinguishability becomes important. So here is a cartoon way of thinking about these atoms. When the atoms are dilute, not a very high density, and the atoms are fast, so they have a short de Broglie wavelength, then these wave functions of the atoms don't overlap. But when the atoms are very cold, so the de Broglie wavelength becomes long, and when the density becomes higher, so that the average distance between the atoms is smaller, then the wave functions overlap. And it is when those wave functions overlap that we get this phenomenon of Bose-Einstein condensation. So this idea that the condition for Bose-Einstein condensation is when the average particle spacing is about equal to the de Broglie wavelength is equivalent to saying that the density of the atoms is about equal to the inverse of the cube of the de Broglie wavelength, or another way of saying it is that the density times the cube of the de Broglie wavelength is about 1. In other words, within a cubic de Broglie wavelength, you have approximately 1 atom. This number is sometimes called the phase space density, and Bose-Einstein condensation happens when the phase space density is about unity. In fact, it's more general than that. Quantum degeneracy in general, quantum degeneracy of a Fermi gas, fermions were not yet understood at the time that all this was being done, but degeneracy of a Fermi gas happens at the same approximate condition. So here are some important points that I want to make about the nature of Bose-Einstein condensation and Bose statistics in general. Einstein did his calculation for a gas of atoms, but not all atoms would be suitable for doing this. Only atoms that are bosons. And bosons are particles that have integral spin, integral in units of h bar, which has the units of angular momentum. So any particle, any atom that in units of h bar has a total angular momentum of 0, 1, 2, and so on, is a boson and will follow the statistics of Bose and has the possibility of undergoing Bose-Einstein condensation. But that's only one of the possible things that can happen in nature. It is also possible to have particles that have half integral spin, that have half h bar, 3 halves h bar, 5 half h bar, and these particles are called fermions. So there are many examples of bosons, hydrogen atoms, sodium atoms, rubidium atoms, photons are all bosons. And there are many fermions, electrons, protons, neutrons are all fermions. So we have both kinds of particles in nature. Only the bosons are going to Bose condense. Photons do not Bose condense, or at least not under any normal conditions. And that's because of the idea that I mentioned before, that if you have a box of photons and you cool it down, the number of photons doesn't stay the same. As the temperature goes down, so does the density of photons, and that lowering of the density prevents the photons from ever Bose condensing unless you do something special, which maybe we can talk about later. On the other hand, everyone knows about lasers. Lasers wouldn't exist if it was not for the fact that the photons in the laser are bosons. Bosons have the property that they are allowed to be in the same quantum state, whereas fermions have the property that they are not allowed to be in the same quantum state. It's all part of what has come to be known as quantum statistics, that bosons and fermions have this very different behavior when you have a collection of many of the bosons or fermions of the same kind. Well, a laser is a large collection of photons all in the same state. That's what makes a laser beam so special, is that all of the photons are in the same state. So in a certain sense, a laser is like a Bose condensate of photons, and people have argued uh, uh, for many years about whether we should think of a laser as being a Bose condensate, and I won't try to settle that argument, but it is a state in which you have many, many photons in the same state, but they're not in the ground state, which is the thing that Einstein calculated for a gas of atoms in thermal equilibrium. So that's another point that I want to make. Real atoms, in contrast to what Einstein assumed, do interact with each other. We can never have a gas that is ideal because all gas atoms interact with one another to at least some extent. So one of the reasons, one of the results of the fact that atoms interact with each other is that typically when you cool a gas of atoms, something else happens. The atoms may condense into a liquid or a solid. They may stick to the walls of the container because of their interactions with the container. So very often something else happens as you cool down a gas, and you have to provide very special conditions for Bose-Einstein condensation to happen. And this is why another one of the reasons why it has taken so long for Bose-Einstein condensation to come about. Now, another point that I want to make is that Einstein did not consider the quantum nature of the motion of the atoms, at least as far as I can see. But typically, we trap our atoms because we want to hold on to them for a long time. And the atoms have certain quantized energy levels within that potential well that traps the atoms. And so we should think of the motion of the atoms in a quantum mechanical way. Einstein thought of the atoms as having different velocities. We would think of the atoms as occupying different energy levels of the potential in which they are held. And Bose-Einstein condensation happens when a large fraction of the atoms go into the lowest possible energy level, which is to say the ground state. Now, over time, people have seen strange and beautiful phenomena and have wondered, do these phenomena have something to do with Bose-Einstein condensation? In 1911, Camerling Onus in the Netherlands discovered superconductivity, sort of accidentally. He was looking at the resistance of mercury as he cooled his sample of mercury down and found that at a temperature near the temperature of liquid helium, that essentially the resistance of the mercury dropped to zero. And this was the first observation of superconductivity. This was years before Bose-Einstein condensation was thought up by Einstein based on Bose's statistics. Years after Einstein came up with the idea of Bose-Einstein condensation, Kapitsa discovered the superfluidity of liquid helium. Liquid helium had been made many years before, but it was the superfluidity was not something that was clearly identified until 1936 by Kapitsa and also by Allen and Misner. And what's seen here, it's a little bit hard to tell what's going on, but there's the surface of the superfluid helium inside this this container, and the superfluid helium crawls up the side of the container and then goes down the outside of the container and drips off the bottom. And this strange behavior of crawling up the side of the container is because of the superfluidity. Now, helium is a boson. And so the question arose, is this Bose-Einstein condensation? And the answer wasn't clear to people. This was not an ideal gas by any means. This was a liquid after all. In the same way, when people started to understand much later, because of the theory of Bardeen, Cooper, and Schrieffer, how superconductivity happened by the pairing of two electrons. The two electrons are fermions, but the pair that the two fermions make is a boson. Is this Bose-Einstein condensation? And well, whatever it wasn't the sort of Bose-Einstein condensation that Einstein was thinking about. So this was in the background when people started to think about, could you make a Bose-Einstein condensate out of an atomic gas? So now, before we go further, I would like to invite you to ask me questions, but I would also invite any of you who know something about the history of the science that we've been talking about to answer whether you know, for example, whether Bose's original English manuscript exists, whether there's any evidence that people like Maxwell and Boltzmann ever thought about different counting techniques because of indistinguishability, and how much did Bose realize about how revolutionary his idea was? It seems quite clear that Max Planck did not understand how revolutionary his idea was. And I'm wondering whether Bose also did not realize in the same way that Planck did how much his idea was revolutionizing physics. And I have a few questions that I suggest that you might ask, but I'm guessing you probably have better questions than the ones that I'm suggesting. So let's have some questions.
Questions from audience?
So
Yes, go ahead.
the article sent to Einstein by certain Bose in 1924, before when that article was sent to Einstein, he sent it to Film magazine. And it, as you said, it was rejected outright from the editorial desk. When Satyam Bose was teaching at the Dhaka University, black body radiation as derived by Planck, he realized there are some flaws. He realized that the 8 pi nu square by c cube, that cofactor in the formula, was not done by quantum mechanically. So it was done classically. And then the other factor, h nu over e to the power h nu minus 1, that factor was done assuming the energy between radiation and the material wall, exchange of energy, that was quantized, not the photon itself.
Yes, exactly.
So that was the flaw he realized, and it was him for the first time, because all Ehrenfest, Debye, Einstein himself, and a lot of other scientists there in Germany, they were trying to explain, to find a proper explanation behind the black body radiation, because Professor Rubin, when he visited Planck at his home for a dinner, he explained to Planck that there is no theory, there is no formula that can explain black body radiation over the whole spectrum.
Right.
So overnight, he found the formula and sent it to Rubin. And Rubin then confirmed that that magical formula worked. So, but it was an educated guess only. So, and then everybody was trying to, because they know the answer, but they don't know how to get to that answer, the proper explanation. So that's why Einstein was so happy when he received the article sent by Satyam Bose. So that was
Right.
my mood.
Well, thank you for that wonderful summary of that history. What I'm wondering is, does the original English manuscript submitted to PhilMag, does that manuscript still exist? Or at least the English text?
Yes, I have a copy, and we have a museum.
Wonderful, wonderful. Now, what I
Yeah.
want to know from you is Einstein's translation faithful to the English text written by Bose, or did Einstein slip in any of his own perspectives?
Okay, there is a one story. Do we have the Partho Ghosh here? Not here. So Partho Ghosh, who is also a participant of this conference, he is a direct student of Satyam Bose. So once he visited his home, so he mentioned that I'm going to tell you something you must not disclose to anybody. So the factor 2 he multiplied. He said to him that factor 2, the reason I explained, was deleted by Einstein. Instead, he said that it is due to polarization.
Huh.
But what Satyam Bose wrote in his original paper, that was due to spin. So photon spin.
Yeah.
So later, C.V. Raman wrote an article, and he mentioned that in 1933, there was an article where he first time proved that photon indeed has spin, and he made the point that through personal communication, Satyam Bose mentioned that I also wrote in my paper the photon had a spin, but Einstein removed that instead. So that was one story.
Okay, okay. Thank you very much. I'm very happy to have that information. Thank you. So,
I just want to add one comment. The fact that it's related to your question, like did Bose realize how revolutionary his idea was? So one thing you can sort of infer from this polarization story that he was thinking of photon helicity in a angular moment, in a spin sense, not in a classical angular momentum sense. So that means to me, what I read into it is that he was more believing into the quantum aspect of photon than Planck, right? So if you think of helicity as an intrinsic polarization state, like quantum version of angular momentum, so from that I'm trying to answer your question to us that I think he was a step ahead of Planck in
oh,
believing.
absolutely. Yes,
Yeah,
he
yeah.
clearly had a much more mature understanding of the concept of
Yeah,
photon.
we had more quantitative evidence for his belief into the quantumness of this through the helicity story.
Yeah, absolutely. Okay, if there aren't any other questions, I'll go on, but I encourage you to think about questions because we will stop again.
There is one question
Oh,
there.
wonderful. Wonderful.
To the best of my understanding, in Bose's paper, there is no explicit mention of indistinguishability as the driving principle. Whether he thought of it is unclear, but all I remember is from some footnote written by Einstein somewhere that Einstein, he did not realize the indistinguishability to be the point of departure, which was pointed out to him in a private discussion by Paul Ehrenfest.
Uh-huh. Well, that's really interesting because without indistinguishability, you couldn't have the counting statistics.
Exactly.
Right.
But Bose does not mention that this is why my results are different. Nor did Einstein realize till Ehrenfest pointed it out to Einstein.
Uh-huh.
This is somewhere mentioned by Einstein. Unfortunately, I am not prepared to, at this stage, here to exactly point you to the source, but it is a footnote somewhere.
Uh-huh. Well, I remember hearing a story that
Yeah.
when Einstein wrote up his idea of Bose-Einstein condensation, that he sent it out to some of his friends, maybe including Ehrenfest,
Yeah.
and he got some responses saying, "You're counting the wrong way." And his response was, "That's the whole point. That's what new about what Bose did." So he understood that he was
Exactly.
counting differently. Mhm.
Exactly.
Okay. Still many things to be learned. Okay, let's go on.
You have this question or comment?
Oh, yes. Wonderful. Yes.
Yeah, go ahead. Yeah.
So you said that in the de Broglie oils of the bosons overlap, the Bose-Einstein condensation occurs. So why doesn't the de Broglie oil of the fermions don't overlap in the same way?
Well, they do, and it produces the strange results that a Fermi gas has. So what happens when the fermions wave functions begin to overlap, then you start to develop the properties of a degenerate Fermi gas. Now, since one of the key features of fermions is that they are not allowed to be in the same state, what it means is that we start to develop what is sometimes called the Fermi sea, where every level from the ground state on up is occupied. And then when you get to what's called the Fermi level, which is the last state occupied by these fermions, then everything above that is unoccupied. Now, that simple picture is what happens when the temperature is zero. When the temperature is above zero, but still in this condition of Fermi degeneracy, what it means is that almost all the states below the Fermi level are occupied until you start to get close to the Fermi level. And then you have a mixture of occupied and unoccupied states. If you're very far from this condition of having the spacing being equal to the Broglie wavelength, then the fermions look like an ordinary gas, just as bosons, if they're very far higher in temperature from that condition, looks like an ordinary gas.
Thank you.
I think you can move on.
Okay,
It's part of the
so,
talk.
right. So, people began to think, can we make a Bose condensate of atoms that does not have any of the questions that we might ask about liquid helium, that is a gas, not a liquid, or a gas of atoms, not something that has paired electron states, which are paired in momentum space, not in physical space. People started to think about this. And in 1976, these two gentlemen, Stoile and Gneisenau, proposed that hydrogen would be an excellent candidate. Now, why? Well, hydrogen is very light. So remember, if the mass is small, the temperature can be higher. So that's good because it's easier to have higher temperatures. Hydrogen is simple enough that people could calculate what the interatomic potential was, and it was known that as a result of the interatomic potential, that the scattering cross-section is small, so the gas is very close to being an ideal gas. And it could also be calculated that if you aligned all the spins of the hydrogen, that is, all the electron spins are pointing in the same direction, then this gas could not form molecules. There's no, the potential does not support any bound state. Furthermore, I'm not sure I've even written it here, it never condenses into a liquid. That is, even at absolute zero, the spin polarized hydrogen remains a gas. So that seems like it's a good idea. So all of these things combined to make people think that this was a good choice. And it turns out that it was not a good choice at all. I was at MIT at the time. My thesis advisor, Dan Klepner, and his colleague, Tom Graytak, looked at the Stoile and Gneisenau paper and thought it was a good idea and asked me to start the experiment. So other groups were beginning this experiment as well. So I started to work on this and do experiments with having hydrogen hit cold surfaces and transporting it around. And one of the things I learned was that if you allow the atoms to hit a surface, then they recombine on the surface into molecules, generate lots of heat, and this is really bad. And then I left to go to where I am now, and other people joined the team and developed some of the key techniques that other people would use to make Bose-Einstein condensation. Those techniques were techniques of magnetic trapping and evaporative cooling, and we're going to return to that. When I went to NIST, I started to work on laser cooling, and there were a few other groups in Bell Labs and in Moscow that were also beginning to do laser cooling. Today, there are hundreds of groups around the world doing laser cooling. And as you heard in the introduction, laser cooling is one of the things that has allowed us to make Bose-Einstein condensation. So let me very quickly review the idea of laser cooling, which I think many of you know about. The idea is that if you have a gas represented here in one dimension, with some of the atoms going one way and some of the atoms going another way, and if you shine in light, and the light is tuned a little bit below the resonant frequency, then because of the Doppler shift, the atom that's moving toward the light will more strongly absorb the light and slow down, whereas the atom moving away from the light will weakly absorb the atom and speed up, but only a little bit. But if you then bring in light from both directions, then atoms in any direction will slow down because they preferentially absorb light from that laser beam that opposes their motion. And if you bring in laser beams from more directions, then it doesn't matter which way the atom goes, it will absorb light from the laser beam that opposes its motion. And this process is called Doppler cooling and achieves temperatures of a few hundred microkelvin, so very cold, but really not cold enough to do Bose condensation. In our group, surprisingly, we found that there are much lower temperatures, and there's a different mechanism, a more subtle mechanism called polarization gradient cooling or subdoppler cooling, which I'm not going to explain right now, but if we have time, I'll be happy to explain it in the question period. But that process produced atoms with temperatures of just a few microkelvin, or sometimes even below a microkelvin. Now, those atoms are often trapped. Now, by that I mean that we use some kind of an electromagnetic field, magnetic field, or a laser field to hold the atoms in place. Because we can't hold them in any physical container, because no physical container can be made as cold as these atoms get. And if we did have such a container, the atoms would simply stick to it. So instead, we use magnetic fields or laser fields to hold the atoms. And here's a picture of one kind of trap for atoms called a magneto-optical trap. It combines magnetic and laser fields, and that little spot of yellow that you see there is a cloud of sodium atoms at a temperature of a few tens of microkelvins being trapped in what is called a magneto-optical trap, which was invented by Jean Dalibard. So the beauty of this is that laser cooling and trapping provide a way of cooling and confining our gas of atoms without ever having them come into contact with a surface. And if they come into contact with a surface, that's where bad things can happen. The atoms can combine into molecules, they can stick to the surface, and so having this ability to keep the atoms away from the surface is very good. And the kinds of atoms we were doing this with were sodium and rubidium. And so you might think that people would think this is a really good way of making a Bose condensate. But in fact, people did not think that, or at least not at the beginning, because they noted that all of these atoms, sodium, rubidium, other similar atoms, form molecules. Their potentials support many, many bound states. And the thinking was that if you had a gas of such atoms, they would just turn into molecules and you'd lose all your atoms and you'd never make a Bose condensate. That's wrong. That criticism was not true at all. And the reason is that you can't form molecules in a two-body collision. If two particles collide, they cannot stick together unless they do some kind of excitation of internal states, and that excitation will come back and break the molecule apart. You can't conserve energy and momentum in the collision of two atoms and have the atoms stick together. So the atoms come in, they collide, they go out, and you still have atoms. Only if you have a third body present. So let's say you have a third atom here, then the two atoms can come and stick together and shoot the third atom out. The third atom can be used to conserve the energy and momentum of the three-body collision. But three-body collisions are not very probable, because it's not very likely that you have a third atom hanging around just at the place where two of these atoms come together in a close collision. And if you reduce the density, that probability becomes even more unlikely. So the rate at which such collisions happens goes at the square of the density, whereas the rate at which two-body collisions happen goes like the density. So if I reduce the density, I reduce the three-body rate, that is the process that can make molecules, very fast, while I don't reduce the rate at which the atoms equilibrate, which is important, as we're going to see, nearly as fast. But there's another problem. Three-body molecule formation is not the only bad thing that can happen. When you have a two-body collision in the presence of light, the light can excite a molecule, an excited molecule, or at least put the atoms onto a molecular potential, and then the atoms will fall down the potential, accelerating until they radiate the light, and now you've got fast atoms that are back in the ground state. So you're heating the sample up by having the light on, and this means that you can't get the density very high. You can't get the density higher than about 10 to the 11 per cubic centimeter. I see there's a minus sign there. That should be a plus sign, and I apologize for that. But you cannot have a dense gas of atoms in the presence of light. So you have to turn off the light. If you want to hold the atoms for a long period of time at densities that are higher than 10 to the 11 per cubic centimeter, you must turn off the light. Remember, I suggested a density of 10 to the 14, 3 orders of magnitude higher. We're never going to get that if we leave the light on because of this property of collisional heating in the presence of light. So that means we have to use something other than light to trap the atoms. So we can't use this beautiful trap that you see here in order to trap the atoms. We have to use something that is more benign, something that will not heat the atoms. And one example of that is a magnetic trap. So here's how a magnetic trap works. Imagine that I've got an atom like hydrogen or sodium or rubidium, and it has one unpaired electron. And that electron could be pointing either up or down in the field because that's the only possibilities for a spin-a-half particle like an electron. If we take the atom on this energy state, so this is energy as a function of magnetic field. One of the electron spins energies goes up as we increase the field, and the other one goes down. Let's take the one that goes up and put the atom into a configuration of magnetic field where right here the field is 0. And so these are two coils of wire that have current going in them in opposite directions. Right in the middle, the magnetic field from the two coils cancels out, so it's 0. That puts the energy down here. And any other place, the field is higher and the energy is higher. So that means this is a trap, as long as the atoms stay in the same state. We'll come back to that. So in our group at NIST in 1985, we made the first demonstration of trapping of atoms in a configuration like that. There's the two coils. We slowed the atoms down by shining a laser beam in the opposite direction of the way an atomic beam was going. And then when the atoms got here, we gave it another pulse of light, stopped the atoms, and then trapped them here. And in those first experiments, we trapped them for about a second. Today, people trap atoms for more than a minute, mainly because they have a better vacuum than we did. Now, there's a problem, which I alluded to before. If the atoms have very low energy, if they're very cold, then they go to the place where the field is lowest, which is 0. 0 is the lowest field here. When the field is 0, the atoms can easily make a transition from spin up to spin down. This is called a Majorana transition. And this prevents this kind of trap from working very well. These two heroes, Eric Cornell at NIST Laboratories in Boulder and Wolfgang Ketterle at MIT, figured out ways of making the trap so it didn't have this problem. So they took the trap that we had demonstrated, and they had different ways of making the trap so that it didn't have the problem. And then using that trap, they did the next thing, which had been suggested by the MIT group of Klepner and Graytak, evaporative cooling. The idea of evaporative cooling is just the same thing that happens when you want to cool down your cup of tea. You blow on it, and what you're doing is you're allowing the most energetic water molecules that are in the tea to escape, leaving what is left behind having lower energy and therefore colder. So we do exactly the same thing. We hold the atoms in a trap. We allow the most energetic of the atoms to escape. And that means the atoms that are left have a lower temperature and settle deeper into the trap, and the atom becomes more dense even as it cools down, in spite of the fact that we are throwing away some of the atoms. So in order for this evaporation to work, we have to have the atoms equilibrate with each other to continue to produce some atoms that have high velocities. So it's really important to have the atoms have collisions that will allow them to equilibrate and form a thermal distribution of velocities. But you must be sure that those collisions happen much more rapidly than any of the bad collisions that will form molecules. So this ratio, you need a good ratio, lots of elastic collisions and very few inelastic collisions, lots of equilibrating, thermalizing collisions, very few collisions that represent loss, for example, the making of molecules. And that was one of the reasons why hydrogen was such a bad choice, because it didn't have a good ratio. Rubidium had an excellent ratio, and sodium wasn't very bad either. And this allowed Eric Cornell and his colleague Carl Wyman at Boulder and Wolfgang Ketterle and his team of people at MIT, it allowed them to make Bose condensates of sodium at MIT and of rubidium in Boulder. And here is a famous picture showing the velocity distribution of rubidium atoms as the gas was cooled down to the temperature of Bose-Einstein condensation. So here was a gas at 400 nanokelvin, broad and featureless. This gas is not Bose condensed. But at 200 nanokelvin, this big spike appears, and that is the condensate. That is the large number of atoms at essentially zero velocity, quantum mechanically, in the ground state of the trap. And then continued evaporation gets rid of most of the thermal background, and you have a nearly pure condensate. And as you cool the atoms, the number of atoms, the fraction of the atoms in the condensate increases, and in the case of a trapped gas, it increases like the cube of the ratio of the temperature to the critical temperature, so that you don't have to cool very far before almost all of the atoms are in the ground state. Well, let's stop here. We're almost done, and here are a few possible questions that you may be interested in. So I'm happy to answer any questions you have now, including questions that might be left over from the first half of the talk. So I'm very eager to hear possible questions. I see someone raising their hand.
Yep. Yes.
Yeah, so I mean, since you want sort of interactions to be low, I mean, why didn't people start thinking about like the inert gases like helium or something?
Well, it turns out that in the case of helium, that you still have the possibility. Well, okay, the main reason is that helium's too hard to laser cool. Okay, so and the interactions, it's not that we want to have weak interactions. We want to have the elastic interactions be very big compared to the inelastic ones. And that might be okay for helium, but we don't have any lasers that can laser cool helium. So that's one of the main reasons why we would reject helium. We also have the same kind of problem with other noble gases. The excitation energy from the ground state of the noble gas to the first excited state is very large, and we don't have lasers that can do that. We do routinely laser cool noble gases, but we do that by first putting them into their metastable state, and then we laser cool from there. And this has been done to make a Bose condensate of helium, but not of ground state helium, but of metastable helium, which is very long lived. And then it behaves like an alkali. So it doesn't have such a small interaction, which is probably good because you want to have lots of elastic collisions. So it's not that you don't want an ideal gas. You see, that's the thing. Everybody thought, when I say everybody, I'm including myself, everybody thought we wanted an ideal gas because that's what Einstein was thinking about. But in fact, we don't, because if the gas was ideal, we couldn't use evaporative cooling, and evaporative cooling is the key to making a Bose condensate. But it turns out that we can have gases that have enough in the way of elastic collisions, but still have very few inelastic collisions, molecule forming collisions, or other sorts of losses, spin flip collisions, so that we can make a Bose condensate. And it's not an ideal gas, but it's close to an ideal gas.
One more question.
Yeah, I have a question about the first point, the issues surrounded about the superfluidity in helium and superconductivity. So my question is, probably you know that after the discovery of the high-TC superconductors, there was that bipolaron theory proposed by Mott and Alexandrov, and they kind of tried to explain the superconductivity in cuprates in terms of Bose-Einstein condensation. To me, it appears a bit surprising that we talk helium superfluidity and superconductivity along the same line. That's because there is a very specific expression for condensation temperature for Bose-Einstein condensation, and for liquid helium, superfluid helium, the equation works quite well, because we get a number, if you do very elementary calculation, something like 2.17 degree Kelvin or something like that. But for superconductors, that formula never worked actually. And now we have hydride superconductors under enormous pressure. Those solids are showing a superconducting transition temperature above 200 degree Kelvin. So my question is, we have a very specific expression for Bose-Einstein condensation temperature, and that never works for superconductors. So why do we talk about superfluidity and superconductivity, connecting them to Bose-Einstein condensation, but the theory actually it doesn't work there?
Well, I agree with you, and that is one of the reasons why I question it. On the other hand, I think that both the helium situation and the superconductivity situation are so much more complicated than the situation that Einstein described, that it's hard to completely rule out that something that is at least similar to Bose-Einstein condensation is happening. Today, for low temperature superconductivity, the picture that many people present is that pairing and Bose-Einstein condensation happen at the same time, whereas that's not true for the high temperature superconductivity, so it doesn't work so well. So I think you're absolutely right. This is not Bose-Einstein condensation, at least not the way that Einstein conceived it. But the question remains, is it still related in some way?
Thank you. Thank you very much. The common point, I think, is there is a condensation. Yeah,
yes, I have a follow-up comment on that. Thank you for the response. So the Bose BEC per se, what kind of what Einstein had in mind in deriving that state, I think this was also mentioned by Bill, that it's weakly interacting, almost non-interacting systems. Now, the thing is, all those numbers you said, that when you try to fit for superconductivity, superfluidity works better, little better than superconductivity, and it completely fails when you come to high TC superconductors. So one way to view this is that starting with superfluids, where you could still think of it weakly interacting. So the formula that is derived for completely non-interacting system, so that it works. Then you look at more classical, conventional superconductors, say S-wave, aluminum, or lead or something. It deviates a little bit. There's still residual interaction, but when you crank up interaction, all those parameters deviate significantly from the original derivation of BEC per se. So the way I tend to think about it is that these superconductivity and superfluidity in most systems are still some sort, it's kind of like condensation of bosons, but not necessarily BEC. So condensation of bosons in an interacting setting, that's why when you try to fit it to the Einstein's formula for BEC, you don't find a match. So then it's along that same line. It's like taking a weakly interacting metal block wave, non-interacting band structure, cranking up interaction. Eventually you'll get Mott insulators, and then you have totally departed from that. So I would say that high TC superconductivity, as Bill nicely pointed out, here even the coherence energy scale and the pairing energy scale is even decoupled. So then you're into a non-perturbative, strongly interacting, non-perturbative regime. So then we don't have an exact expression for that. So this is a theoretically open frontier.
And another point is that in liquid helium, the condensate fraction, which can be measured at least approximately using neutron scattering, is no more than 10%, even at absolute zero. Whereas in a rubidium gas, that fraction that is condensed can be 99%. So it's very much closer to Einstein's idea than liquid helium, but it still has pretty strong interactions.
Yeah. So we have one last question before we move on. Yes, please.
Yeah. Thank you so much for the great talk. Just to talk again about the strength of the interaction, could you say a little bit more about that? Particularly, what is it that makes rubidium so good?
Yeah. So the thing that makes rubidium so wonderful, in my opinion, is that it has extremely low inelastic collisions. And this is because of an accidental correspondence between the triplet and singlet scattering length. So it has very little possibility that when the atoms come together, that they will pick up a different phase on the singlet and triplet potentials and come out with the spin flipped. That almost never happens, very low probability. And that's why I've said that rubidium is God's gift to Bose-Einstein condensation. Now, what's the nature of the interactions? So one of the things that happens is that you can have what we call a quantum depletion of the condensate. And in the case of things like rubidium and sodium, the interaction is weak enough that that depletion at absolute zero is only about 1%. On the other hand, the interaction is so strong that it completely dominates the shape of the ground state. If the interactions were zero, then all the atoms would be in the ground state of the trap, and a typical size for that state might be a few micrometers in diameter. But because of the interactions, which are repulsive, the atoms are spread out over a much bigger region of space so that the diameter of the cloud, because of the interactions, these repulsive interactions, is on the order of 100 microns instead of just a few microns. So in one sense, the interactions are quite small. That is, they do not deplete the condensate. But in another sense, the interactions are quite large in that they distort the shape of the cloud so that the interactions are practically the only thing that's important.
Okay, thank you. So you have any, you want to go beyond the questions, or Bill?
Well, looking at my my cell phone, I see that it's 3 minutes after the time we were supposed to stop, and so I don't want to take any time away from the next speaker. But I do want to thank all of you for your engagement in this talk, and for your questions, and for your answers. I'm very pleased and so happy that I could be with you for this time.
Thank you, Bill. Thanks a lot for joining us. Okay, so we move to the next step. No, okay. Oh, we have the speaker also online. So the next talk is by Bong Zhao.
Hello, so can you hear me?
Gases with dipolar interactions in two dimensions. Welcome. You may begin.
Okay, so let me make sure you can hear me well there.
Yes.
Okay. Right. Yeah, so thanks all the organizers for putting it together. Yeah, this is Gyubung from HKUST in Hong Kong. So I'm very honored to be this event that celebrates the contribution by Bose in past more than 100 years. And today, after following the Bill's talks, I'm going to talk a little bit more about this the cold atom experiments based on this Bose contributions. So especially as Bill mentions, in our community, we can prepare this ideal Bose and probably also Fermi gas using the laser cooling and other techniques we have developed in our community. But I'd like to provide a little bit more richer landscapes, how we actually study other physics by using Bose gas with the very exotic interactions or in other contexts. So the first half of my talk, I'm going to talk about what happens if you put the Bose gas or bosonic atoms in the two-dimensional the trap, especially with the dipole-dipole interactions, which is quite unconventional situation we can study. But towards the end of the talk, I'm going to switch a little bit to other topic with the fermions. But what's interesting here is if you have a particular fermions with the different flavors, we actually expect to see the bosonizations, at least in the thermodynamic sense. So this actually will give some sense how the foundational work by the Bose will contribute to different directions. So before I dive into the experiments, I would like to thank our team, especially the students with this the name highlighted in green contributes all the experiments I'm going to present from my group. All right, so as Bill mentions, the cooling the atoms into all the way down to the almost zero temperature is quite unique technique common in the cold atom community. So as Bill mentioned, we start from the very hot metal and we use the laser cooling or other techniques. We prepare the atomic gas, usually the Bose gas in our community, near tens of nanokelvin above the absolute zero temperature. And this is the starting point of the all different experiments or theoretical works where the quantum mechanics is quite important. Here I put the image with the bosons, but we can also cool down the fermions by using similar techniques we have. Also molecules as well in our community. So this is the snapshot of the real laboratory. So we typically have the vacuum chamber in which the atoms, either bosons or fermions, are laser cooled or evaporative cooled. And in the middle of the chamber, you can prepare very cold sample all the way down to the tens of nanokelvin. And this is the starting point of the experiments. But of course, Bill mentioned how we prepare the ideal Bose gas, or at least the weakly interacting Bose gas. But for past few decades, after Bill and his colleagues developed all these techniques, we actually simulate different quantum materials, quantum matter, by putting different atoms and different isotopes into the different contexts. So this is just a few examples that just my group focused on, but in the whole community, there are so many different topics the people try to simulate and understand. Particularly before I discuss the Bose atoms in the 2D, you can also put this atomic sample after cooling, either bosons and fermions, even into the topological context. For instance, we can realize a very special type of the band structure, even the Hermitian or non-Hermitian regime. So I'm very pleased to say that as Bose developed his ideas, of course, in the Hermitian regime, but these days we are the techniques are within our reach that we can put the bosonic particles or even fermionic particles into the open quantum system in the context of the non-Hermitian regime. So in case you're interested, I'm more than happy to discuss in the Q&A session about these directions. Okay, so let's come back. So as Bill and other speakers mentioned about this quantum statistics, we all know that the particles are classified into the two types of particles. One of them is the bosons, the other is fermions. And the destiny of those particles are very well known at the moment. The Bose gas or bosons, they try to be in the same quantum states, while the fermions, they stack up, forming the Fermi sea. But particularly in the cold atom context, or the experiment I'm going to present, you can imagine something between by putting several copies of the fermions. So what I mean by here is you look at the figure in the middle, you see the different color of the fermions, not just red. You see the green, blue, or yellow. So these copies just represent the different spins or different flavors, but under the condition that there is a so-called the SUN symmetry. So if you look at this multi-component Fermi gas, maybe the property of this multi-component Fermi gas or fermions could be maybe in between the bosons and fermions. And this is the second topic I'm going to present in my talk in a minute. So the first part, so this is the outline of my talk. I'm going to present two different topics. In the first part, we'll just put the bosonic atoms into the two-dimensional case, but with the dipole-dipole interactions. So this is a somewhat very unconventional approach, because in the usual case, as Bose consider his theory, we start from the ideal Bose gas, considering, for example, the Bose-Einstein condensations, and people start to put the weakly interactions into that situation. And as long as the interaction is weak enough, we can understand based on this Bose picture or other the frameworks we understand. But those weakly interacting Bose-Einstein condensates is usually assumed that we have a short-range contact interactions in the system. But what if you have a long-range dipole-dipole interactions, and what's the fate of the quantum states or quantum phase we have, particularly in the two dimensions? So this is the first part I want to discuss. And second part is about these fermions with the different flavors on the SUN symmetry. So we'll come back to these points in a minute. So for the first part, let's imagine the bosonic atoms in the two-dimensional setting. So this is a very ideal case. You have a large two-dimensional trap, which is represented by this light blue in these slides. And I put those bosonic particles. And if nothing happens, those particles are a coherence, and which doesn't represent anything. It doesn't reveal any quantum properties. But in what situation maybe the superfluidity emerge in this two-dimensional case? But for the specialist, the answer is very clear, because thanks to the Mermin-Wagner theorems, I mean, we don't expect any long-range order in this two-dimensional case. But especially in the atomic realization of this two-dimensional case, we always have a finite size of the trap. As Bill mentions, we can use the magnetic trap, or you can use the optical trap we can create by using the laser lights. So in this case, we still expect the occurrence of the Bose-Einstein condensation, which is not the case in the ideal 2D. unless you have an absolute zero temperature. So that's about the Bose-Einstein condensation in 2D. But on top of that, the situation gets more confused because according to this so-called the BKT transition frameworks, we still expect the emergence of the quasi-long-range order even in the two-dimensional traps. So the idea is quite dramatic because when you control the temperature in this two-dimensional case with this weakly or interacting Bose gas below this critical temperature, we still expect the occurrence of the superfluids because of the pairing between this vortex and anti-vortex pairing under these BKT scenarios. So this BKT superfluid or BKT scenario has been actively studied in the atomic two-dimensional case over the almost 2 decades. For example, people in the researchers in our community, they put the bosonic Bose-Einstein condensates in the two-dimensional trap they create by either using the laser light or magnetic trap, and they measure the vortices or scale invariance or coherence properties or long-range order as a quasi-long-range ordering, etc. Very well, and we have a very good understanding of this. But interestingly, most of the work, all of the work so far in this two-dimensional Bose gas have been done with the short-range interactions, especially the rubidium atoms that just Bill mentions, or lithium atoms or potassium, or sometimes the sodium atoms. So in all of the cases, we have always the short-range interaction as well only. But recently, we actually start to generate the Bose gas in a 2D trap with both short-range interactions and the dipole-dipole interactions. And this is the very interesting situation because you can revisit this BKT scenario in the presence of the dipole-dipole interactions. So as I just said, in the usual cold atom sample, we have a short-range interactions, which is usually repulsive, but could be tunable towards the attractive case. But what if you put the long-range and anisotropic dipole-dipole interactions into the atomic gas? So this is one way we can deviate from this ideal Bose gas. But it turns out that it's actually make the system very rich. And very recently, people in our community, they start to find and discover quantum droplet, which is the liquid type, the quantum phase, or even supersolids in the system of this dipole-dipole interactions with, the bosonic atoms with the dipole-dipole interactions. And this dipole-dipole interaction is long range, so you can make this Bose-Hubbard model in the lattice system more richer. And people also can make the particles entangled by using these dipole-dipoles. So along this line, we are trying to understand how these two-dimensional dipolar superfluids behave in the context of this BKT scenarios in our experiments. And this is particularly quite interesting in these days because our colleagues, for example, at MIT or GLR, they start to produce the bosonic particles, either atoms or molecules, in a 2D single layers or multiple layers. And we know and we learn how to control or shield the particles from these dipole-dipole relaxations, which is the enemy of our experiments. And particularly at MIT, by Wolfgang Kettli, they start to put the the bilayer of these dipolar Bose gas very close to each other. So these dipole-dipole interactions may allow us to communicate between these two adjunct layers, which is another opportunity we can do. So now it's time to understand the fate of this dipolar bosons in the 2D, even in the single layers. And this is our strong motivations. And of course, this the BKT transition in the dipolar 2 dimensions has been also considered even in the condensed matter setting, such as the exciton fluorescent systems. The only downside of this realization is because intrinsically, whenever the excitons exist in the 2-dimensional electron gas, this dipole direction, the direction of the dipole of the particle, this quasi-particle, is always perpendicular to the 2-dimensional plane. So unless you tilt this dipole angle, it's hard to introduce this anisotropy or attractive part of this dipole-dipole interactions, which is the limitation of these exciton systems. But in the cold atoms or neutral atoms, as Bill mentions, we have the spin degree of freedom or motional degree of freedom, but essentially we can control everything in the lab environments. So what we can provide in this context is very clear. If you prepare this 2-dimensional trap with the dipoles, which is represented by these orange arrows, you can just polarize all these dipoles as you wish by rotating the lab magnetic fields, because the dipole usually align to the external magnetic fields we applied. So you can just tilt the dipoles from the in plane to the out of plane as we wish. And this is how we systematically study this dipolar 2D sample. So this dipolar system has been very well studied, at least theoretically, until the experimental part is within our reach. So if you look at this theoretical curve, the vertical axis is dipole strength, and the horizontal axis is dipole angles. And if you have a very strong dipole-dipole interactions, we naturally expect the emergence of the crystals. But in our case, because we are using still the alkali atoms, or alkali or the lanthanide or magnetic atoms, our dipole-dipole strength is relatively weak compared to the other candidates. So in this phase diagram, we are still studying almost the horizontal line close to the zero. So dipole strength is relatively weak, but we can tilt the dipole angle alpha. So we like to investigate how this BKT scenario change when we tilt the dipole angle or even temperatures. So this is the reason we are exploring at the moment. So this is about the actual experiments. The details is for specialists, but the key idea you want to remember is we just put the Bose atoms into the 2-dimensional trap represented by this green box. But just remember, we just tilt the dipolar angle theta according to this the vertical axis z as you wish. So when you change the theta from 0 to 90 degrees, we would like to understand how this dipole, how this BKT superfluid or BKT transition change. But the first thing we have to do is because this dipole-dipole interactions, UDD, is essentially and mathematically can be decomposed into the two parts. The first part is the delta function, which is same as the contact interactions. So the second part is represent the non-local parts, which involves the second derivative of this one over all potential. And this actually allows us to approximate this 2-dimensional coupling parameter G effective, which determines the fate of this BKT superfluids or the Bose gas in the 2-dimensional case. Well, we have a two contribution. The first one, AS, comes from these normal contact interactions or S-wave contact interactions. So second part is coming from the dipolar parts, which just comes from the contact part of the blue circle in this approximation. So for the time being, we are going to ignore these non-local parts, but we'll come back and see how it emerged. So the first thing we can do is when you tilt the dipole angle theta, we actually tune this G effective, as you see in this simple formula. So if you change the theta, we change the dipole we change the two-dimensional coupling parameter G effective. And this is the we immediately see in the real experiments. So in the cold atom experiment, we have a different proof techniques, but one of them is you can directly look at the density distribution of the atomic sample. So in this, the graph on the right-hand side, we take the in situ density distribution at a different angle theta from 0, the perpendicular, to the in planes. And as we expected, when you change the theta from 0 to 90 degrees, this G effective just decrease. And what you immediately expect is, because your sample is getting weakly interacting with a decreasing G effective, we expect to see the smaller atomic sample or a little bit higher density in the middle. And that's exactly what we see in the real experiments. But of course, you can quantify more. So another way we can detect this two-dimensional superfluid is based on this momentum wave functions. So we can directly measure how this particle distributes over the momentum space. So if you do it correctly, you can measure this momentum wave functions below and above these critical points of this BKT transitions. You can directly measure the coherence developed over the sample. So G1, this is the G1 correlation functions, actually tells how this coherence emerge within the sample. And as you see, in the BKT superfluid regime, we have quite quasi-long range coherence, which is represented by this polar decay of this G1 correlation. This is exactly what the BKT scenario tells us about it. But below the BKT transitions, we start to see the exponential decay of this correlation, which presents there is no long-range coherence at all. So we can also measure this atom number, how many atoms we need to have this superfluid. And all the results we have here is very consistent with the previous measurements, which follows the simple formula that I put here, G effective. First part comes from the S wave, the second part coming from the dipolar contributions. So so far, it seems quite good, because even though you have a dipole-dipole interactions, our system still follows this BKT transitions. However, you may ask, where is the long-range effects? Because we know the dipole-dipole interaction is long-range, so there must be the effects we would like to see. And to answer these two questions, we actually come back and look at this in situ density distributions. And we can actually take the average data and analyze and get this so-called equation of states to extract all the thermodynamic properties. And based on our simple Gross-Pitayevsky simulation, we understand how this in situ distribution change, and this graph tells us how well we understood the system evolve. With all together, we are ready to look at this so-called phase diagram or equation of states measurements. So the graph, it looks a little bit complicated, but just remember, in the horizontal axis, we have a chemical potential. In the vertical axis, we measure the phase space density just Bill mentions within the atomic systems. And by differentiating actually the phase space density with the chemical potential, based on our simple thermodynamic relations, we can measure this compressibility out of this superfluids or dipolar superfluids. And when you change the angle theta from 0 to 9, you can identify when this BKT transition occurs at a particular or critical chemical potential. And this is how we measure, and which still follows the simple relation we had in mind, which is represented by this blue curve. So far, still this chemical potential measurement does not require the long range effects. It's still well captured by these our first order approximations. Then the last question you have, okay, so where is the non-local effects we have, which is represented by this red circle. The answer is yes, we have a non-local effects, which should be in these quantum systems. And if you look at the phase space density measurements as a function of the chemical potential more carefully, there is a non-local effect, especially in the deep BKT superfluid regime. So if you look at this graph, there is a 0 in the middle, the horizontal axis, which represent where the BKT transition occurs at a particular chemical potential. Below this chemical potential, we have a multiple curve, which represents the different angle. So essentially, we tilt the dipole from 0 to all the way to the in-plane 90 degrees, and we just collect all the data. And it turns out that below these critical points, they all collapse into the single curve, which means there is some universality still exists below these 0 points. But above these critical points, when you get into the deep superfluids, depending on the angle, the curve starts to deviate from these red dashed lines, which is the Thomas Fermi limits, or this is the well-known results for this repulsive or contact interacting BKT superfluids. So if you look at data carefully, when you tilt the dipole angle all the way to the 90 degrees, it starts to deviate a lot, especially 70 degrees or 55 or 70 or 90 degrees, the slope change, which is actually because of these non-local effects. And if we actually do some simulation, including this dipole-dipole interactions using this Gross-Pitaevsky simulations, we actually capture this deviation, although it's not perfectly matched yet, but the direction is still well captured. And this is the evidence of these non-local effects. So the message we have here is, well, when these dipole-dipole interactions exist on top of these contact interactions, plus, I mean, in this ideal Bose gas, well, this BKT transition still capture the physics in the sense that as long as we understand this effective coupling parameter well enough, this BKT superfluid still exist. Just because our dipole-dipole interaction is not strong enough in this context. The last thing I want to present about this topic is this is dipolar superfluid, so there must be anisotropy. And one thing we can directly measure is the compressibility measurements based on this number fluctuations we do in our measurements. So in the graph on the left-hand side, we tilt the angle and we measure how the atoms fluctuates within the small box we characterize. That's directly related to the thermodynamic compressibility based on this dissipation fluctuation theorem. And our sample, our superfluid, intrinsically has the anisotropy because of the dipole-dipole interactions. And this compressibility, surprisingly, is different depending on the proof you prepare within your sample. And this is the key feature of this dipole-dipole superfluid. All right, so this is the first part of my talk. So I have only a few more slides about this, the second topic of my slides. And if I'm correct, probably I have 10 more minutes. So I'm trying to finish quickly and then take some questions. So, okay, so steering the gear. So the second topic, I'm going to actually present another set of experiments with the fermions. But these fermions are quite interesting in the sense that we have the SUN spin symmetry. And as I explained, I have multiple flavors or multiple spin components, but they interact all identically. And the figure I present here is I can tune single component or 2 components or 3 components all the way to the 6 components Fermi system. And when you increase the number of components, we expect the system thermodynamically bosonized because the fermions start to talk each other like the bosons do. And the question is, how do we actually rigorously prove that this bosonization process happens in this Fermi gas system? And that's what we answer in our experiments. Especially for having this kind of system, we use a very special type of atoms, so-called the alkali Earth-like fermions, which is slightly different from the rubidium or other alkali atoms, because we have two electrons, the valence electrons, as described by this red dot. And the consequence is quite interesting because of the two electrons in the valence bonds, the total angular momentum will be 0, which means the electrons are pretty much decoupled from the nucleus. And the result is quite interesting because if you write down the Hamiltonian of such fermions, you have a kinetic terms, but at the end, there are multi channels for describing the two-body collisions. But it doesn't matter what configuration you choose, but the scattering properties is always identical, which is why this system satisfies this spin permutation relations for this SUN symmetry. So the simply saying, in this Fermi gas system, any two pair collide identically in any spins. So in this situation, you can think about the change of the statistics in a quantum many-body setting. I mean, one of the famous example we know is actually the fermionizations in the one-dimensional bosonic system. So if you put the bosons in the one-dimensional case, and if you crank up the interactions between the bosons, they start to behave like the fermions because they cannot penetrate each other's, and your wave function can be described by the fermions to describe the resulting phase. In our case, the situation is a little bit different because we start with the fermions, but I increase the number of components of my Fermi system from 1 to 2, 3, all the way to the large numbers. And in these situations, if you imagine the Pauli exclusion principle, I mean, because of the presence of the other counterparts, different flavor, this Pauli exclusion principle becomes more inefficient as a function of number of components. And that's what we call the bosonizations. And this situation actually has been tested in different contexts in the cold atom experiments. For instance, people put this multi-component or multi-flavor fermions in the one-dimensional case, and they actually measure this collective mode frequency and showing that it approached to the bosonic case, which is represented by this black curve. This is earlier works, very nice start of this business. Another one is you can also measure the similar collective modes, not in the 1D, even two-dimensional case. So in both experiments, by measuring the collective mode frequency, we have a very strong but indirect evidence that the bosonization happens. But the one open question is, this bosonization is about the thermodynamic properties, but there are many, many other thermodynamic quantities we are supposed to measure. So how do we say that this bosonization occurs for all different thermodynamic observables? And of course, there is no good way to prove rigorously, but luckily, in recent days, there is one new parameter, so-called the contact parameter, that actually govern and determine all different kinds of thermodynamics, as long as your Fermi gas or Bose gas interacts in the very low density regime. Oh, sorry about it. So there is some ping I have. So we actually take this approach to measure the thermodynamic properties and show that the bosonization happens. So how do we measure this? Well, we actually take this atomic gas and the way we measure this, the contact is based on the high momentum tail of this atomic distribution in the momentum space. So in the real data, if you take the atomic distributions, there are few atoms out there, out here, which represent the very high momentum of the atomic's original quantum states. And we actually take all different techniques to take any signal existing there. And finally, you can measure, for instance, some meaningful signal out there. And the height of this signal is so-called the contact. So this is the new approach to measure this universal parameter contact out of this atomic system. And as long as this contact becomes bosonized, we can tell that all the thermodynamic quantity should bosonize in this SUN fermions. And if you imagine how this contact must scale as a function of the number of components. So for the single components, you have a one Fermi C, and this total contact, which represent how these Fermi C interact with each other. And there is no interactions because there's no counterparts. If you have a two Fermi C, they interact, and the number of atoms times number of atoms, so only one pair, so 2 minus 1. And if you go to the ends, this contact that represents how these Fermi C talk to each other is proportional to the m minus 1. And that's exactly what we can measure out of our contact interactions. And if you measure this contact as a function of number of spin components in our system, which range from 1 to 6, the contact we directly measure is linearly increased as we expected. That follows the n minus 1 scaling. So these measurements actually allow us to argue that this is a very rigorous experimental verification that this bosonization happens, especially in the three-dimensional case that we are working right now. And especially in 3D, it's very difficult to numerically calculate or analytically prove this bosonization must happen, which is different from the 1D case, which we can calculate. So again, the horizontal axis, we have a number of spin components, and we measure the contact, and this contact is approaching to the bosonic limit, which is clearly shown in our experiments. And this is actually the first verification of this bosonization in our three-dimensional case. Okay, so I came to the last slides. And again, I'm very happy to be the part of this very meaningful event. And I hope I can share how this cold atom community make the very foundational work by Bose rich enough by putting different Hamiltonian terms, different context. And I hope you enjoy the work we are representing today. And I'm more than happy to take any questions from audience. Yeah, thank you so much.
Thank you very much for a wonderful talk. Questions? Yeah.
Hi, that was a wonderful talk. So I just wanted to know that BKT transition typically characterized by the essential singularity, and the other one is order disorder, symmetry breaking. So how do we characterize the Bose-Einstein condensation? Is it, so do we know whether the correlation length have essential singularity or not? Or is there any similarity with the BKT transition?
Yeah, actually, that's a wonderful question. So I didn't explain the details in the atomic system because especially in the atomic realization of the BKT in 2D is quite subtle. There are multiple reasons, but one of them is Bose-Einstein condensation and the BKT transition always come together. So especially in the experiments, it's really difficult to distinguish which one comes first. We know that BKT superfluidity is fully interaction driven. Without the interactions, we don't expect any the BKT transitions. However, the Bose-Einstein condensation it can occur even in the ideal case. But of course, in the two-dimensional case, in the ideal 2D, there is no Bose-Einstein condensation except the zero temperature. So, but of course, we have a finite trap which also supports the existence of the Bose-Einstein condensation, even in the 2D. So the long story too short, I think these two concepts, BC and the BKT transition, they always come together. So ideally, as you just mentioned, the singularity measurements may allow us to pinpoint which one comes slightly first or later. However, in the current stage of the experimental technique in our community, we are not there yet to pinpoint which one comes exactly first and second. But that could be good way we actually think about for the future directions.
Thank you.
Yes.
So in this, you said that the stiffness has like some anisotropy. So is this? I guess there's no crystalline structure. So is this related to the fact that the polarization field which somehow couples with the density field? Is that the reason why you get an anisotropy?
Oh, maybe the best way you think about the reason behind is we have a BEC essentially. So you can imagine the Bogoliubov excitation spectrum. But without the dipole-dipole interactions, this spectrum is always isotropic. But now you have a dipole-dipole interaction, especially tilted dipole, this Bogoliubov excitation spectrum will be anisotropy. So the sound speed of sounds depend on the angle. So that's exactly why the compressibility is not identical along the x-axis or y-axis. It depends on the propagation axis or directions. So essentially, your Bogoliubov excitation spectrum has the angular dependence within your two-dimensional sample.
Any other question? Yes.
So I'm new to Weinberg-Marmin and Wagner theorem, and to my understanding, it says that we cannot have Bose-Einstein condensates in an infinite setting for d equal less than 2, so dimension equal and less than 2. But if I understand your talk correctly, you are talking about condensates in 2 dimension. So how is this different? What makes your case possible?
Oh, I mean, in this, yeah, but I mean, this theorem actually excludes the occurrence of the long range order, right, in 2D. But in our atomic system, but that doesn't like exclude this BKT transition, right? BKT only we support this quasi long range order in the particular case. And another aspect you think about is we are not putting the atoms into the real two-dimensional case. We always have the quasi two-dimensional case with a finite size of the trap. And that's the real realization of our two-dimensional sample. So even though we call it 2D, we still support the Bose-Einstein condensation in our two-dimensional trap, which we actually probably celebrate the Bose, because theoretically there's no BC transition in the 2D, but in the atomic realization of the two-dimensional case, we actually have a Bose-Einstein condensation because of the presence of the trap, the finite size trap, or the non-zero thickness of this vertical axis.
Okay, thank you.
I have a question on the bosonization or fermion boson crossover you're probing in 1D systems, where you said you observe collective modes evidence for that. Was it 1D or 3D?
That collective measurements, this is the work by the Italian. They actually put this multi-fermions in the really 1D regime. And they measure either collective mode, they also measure the momentum distributions.
Mhm.
And based on their calculations, I mean, they start to see the deviations, I mean, above this, the Luttinger gas calculations.
I see.
This is the data. Yeah,
Why
sorry.
I wondered whether this collective modes have polarization, or you could build up a model to make them having polarization states of these collective modes, or
Oh, yeah, I mean, condensed matter language has a polarization, but in the atomic language, I think we can imagine different order of the collective modes we can measure.
uh-huh.
So here they measure the breeding modes, which means the whole volume just increase and shrink and increase back and forth, and they measure the frequency. But as you said, you can also measure different order of the collective, like quadrupole or octupole, and so on and so forth.
Yeah, that's wonderful. Thank you so much. Let's thank the speaker once again.
Yeah, thank you so much.
Thank you for being with us. Okay, so this concludes the session. Now we have a tea break. Okay, so we have a tea break for 15 minutes or so.